Okay, let's get into it. Today we are doing a deep dive on a piece of gear that solves a massive headache for anyone designing AV
A
systems.
true nightmare, really.
Hmm.
You're trying to send a perfect high-resolution video signal a long way,
Hmm.
and physics just gets in the way.
Exactly. We're talking about the DVIgear DVI-7317 4K HDMI fiber optic extender.
Right, because with the standard copper HDMI cable, you hit a wall, what, 50 feet maybe? If you're lucky.
If you're very lucky. So this thing, the DVI-7317, just bypasses that problem completely.
It does. It takes your HDMI signal, converts it into pulses of light at the transmitter end. The TX sends down a fiber optic cable, and then the receiver, the RX, just turns it back.
And it's not a cheap solution, but it's for when you need reliability. The set is about $698.
It's an investment, yeah. But what you get for that is some serious capability. It's HDMI 1.4 compliant, handles up to 8-channel LPCM audio.
And the big one, 4K resolution. But there's a key detail here for anyone listening, right? A trade-off.
A very important one. You can get a full 4.4.4 color signal, perfect for PC graphics, but only at 30 frames per second.
So 3840 by 2160 at 30p.
Yep. If you want that really smooth 60 frames per second, you have to accept a bit of color compression down to 4.2.0.
And that's a decision every system architect has to make. But for me, the most fascinating part is how it does all this. We're talking about a single strand of fiber.
Just one, an LC-terminated fiber.
Which seems kind of impossible. Don't you need one path for sending and another for, getting information back for the handshake?
You'd think so. But this is where the really clever engineering comes in. It uses something called wavelength division multiplexing, WDM.
Okay, break that down for us. WDM.
Think of it like a highway. Instead of building two separate roads, you just create different lanes on the same road using different colors of light.
So you're sending different data on different wavelengths, all down the same physical fiber.
Exactly. The main video signal, which is a huge 10.3 gigabits per second, that travels from the transmitter to the receiver on the 1310 nanometer wavelength.
Okay, so that's the high-speed lane going one way, but what about the traffic coming back?
Right, you still need that reverse path for all the control data.
For things like eDIVE and HDCP, right?
Precisely. That's the slower lane, just 250 megabits per second, and it travels from the receiver back to the transmitter on the 1550 nanometer wavelength.
So the display can still tell the source what it's capable of, and the copy protection can do its handshake.
And it all happens simultaneously on one tiny strand of glass. It's incredibly efficient.
And the physical advantages are huge, too. These things are tiny, like less than an inch wide, and they weigh almost nothing.
Plus, because it's light, not electricity, it's completely immune to environmental noise. You get zero RFI or EMI interference, which is non-negotiable in, say, a hospital or a control room.
Okay, so that's the engineering. But there's another almost shocking trade-off hiding in the specs here, and it's all about distance.
This is the real gotcha that people need to know about. It all depends on one thing, whether you need HDCP.
The content protects.
Yes. If your signal has to be encrypted with HDCP, your maximum distance is capped. A hard stop. It's 1,000 feet, which is about 300 meters. And it doesn't matter what kind of fiber you use.
1,000 feet. Why? Why does turning on copy protection slash the range so dramatically?
It's all about timing. The HDCP handshake is a constant back-and-forth conversation that's extremely sensitive to latency. Over extreme distances, the signal timing degrades just enough to break that handshake. The protocol simply won't allow it.
So the security check itself limits the physical distance.
That's it.
So let's flip that. What happens if you're sending a signal that doesn't have HDCP? Maybe from a security camera or a scientific instrument.
Well, without that HDCP burden, the gloves come off. The potential distance just explodes.
How far are we talking?
On standard OM4 multi-mode fiber, you can go up to 2,600 feet. But if you use single-mode fiber, you can push that signal up to 1.2 miles.
Wow.
About 2,000 meters. It's the difference between wiring up a concert hall and connecting two separate buildings on a campus.
So, to wrap this all up for you listening, this DVI-7317 is a brilliant piece of WDM engineering. It lets you send 4K over a single, noise-immune fiber strand. It's even flexible enough that the transmitter can be powered from a USB port.
It's an incredibly powerful tool,
Yeah.
but it brings up this really fundamental design question.
Right. And that's the final thought we want to leave you with. How does the simple requirement for digital content protection force you to completely rethink your physical architecture? When a security check can shrink your maximum reach from over a mile down to just 1,000 feet, well, that's a constraint that defines the cutting edge of system design.